Okay, we were to an interesting integral. We've got the integral from 0 to 1 of sine squared ln x over ln x dx. Okay, so the first thing I notice on it is just that we've got natural log of x in two places. Let's try to clean that up with a u substitution. But I think what I want to do, instead of just doing this, let's put a minus sign on it. That way it's going to help. That way our balance won't go to minus infinity. It'll go to infinity. So let's use that. And then let's actually solve for x. So if we have minus u equals ln x, isolating x, we get x equals e to the minus u. Take a derivative, dx is going to be just minus e to the minus u. Go ahead and substitute. So take a 1, ln 1 is just 0. Plug in 0, we get minus infinity times a minus sign. So now we get positive infinity, and that's why I wanted that minus sign there. And then in order to set this up and make it a little easier, I can put a minus sign on that so that we get a u, and then we should have a minus sign out front. And then notice I can do the same kind of thing in this numerator without changing it, just because if we look at it like this, sine ln x, and this thing's all squared, well, I can take this minus sign out front because it's an odd function, so that's going to change that to just a plus, or that goes away. But when you square it, the minus sign here is going to go away, and we just get back the original thing. So doing this doesn't change it. So then substituting in the numerator, this is just going to become sine squared of u. And then here, this will just be a u. And for dx, we have minus e minus u du. And sorry, I forgot the du over here. I think it was one of my first videos where I forgot the du and someone said they wanted to claw their eyes out, but hopefully I put that back in time before anyone had to claw their eyes out. And then over here, let's take this minus sign, and I can use to flip the bounds. We'll leave this minus sign in front. And now with this here, you'll notice it's pretty close to being set up as a Laplace transform. All I need to do to parameterize this, let's write this here as e minus su. And we can define this as some function, f of s, where when we get back to our solution, we're just going to want f of 1 when s is equal to 1. But now here, it's a little tricky to get the Laplace transform of something when we have sine squared, just because I don't have a formula for that offhand. So using our definition of the Laplace transform, we want the Laplace transform of this, but let's reduce it first using the power reduction on sine squared. So for that, for sine squared of u, I can write that as 1/2 1 minus cosine of 2u. So let's rewrite the integral just using what we have right here. And so now for this thing right here, we reduce the power, and what we're going to want is the Laplace transform of 1 minus cosine 2u over u. The interesting thing about this is if you separate this into two integrals, breaking it on the minus sign, individually these integrals would diverge, but doing it this way, keeping it together, this should work out just fine. So what we're going to need first on this before we take this whole Laplace transform is we just want the numerator, because we have a formula for this that we'll see in a second. But I just want to take the Laplace transform of 1 minus cosine of 2u. I can break this up into two Laplace transforms now. We can take the Laplace of 1 minus the Laplace of cosine 2u. Well, for each of these, we've got formulas we can use on it. First, for Laplace of 1, I mean, you could just remember Laplace of 1, but you could also do it with this, thinking of it like a polynomial, like if we had x or t to the 0, where n is 0, then using this when n is 0, this first part is just going to be 1 over s. And then for the second one, using this formula here, we're going to have s over s squared plus a squared, where the a is 2, that's going to be a plus 4. But now here where we're dividing by u, we've got a different Laplace transform formula for this. If we have something like the Laplace of f of t over t, this is kind of an unusual formula where they give us the solution in terms of another integral. So this is going to be big F of u du. And so in order to do this, the big F of u is just going to be the Laplace transform of like the f of t, which is just this numerator here, which we just found. This is going to be our big F of s. So in order to get this value, all we need to do is a variable change this to u. So for this whole expression here, we're going to have the integral from s to infinity. Take this and change this to u, so it's just going to be 1 over u minus u over u squared plus 4 du. Integrating all this stuff, we'll get natural log of u. I'm dropping absolute value because we're assuming the u value to be greater than 0. Then for this next part, on this one we can do this on the fly. If I multiply in 2 and multiply by 1/2 in front, then we've got the derivative This way the derivative of the denominator is just in the numerator, so this is going to be minus 1/2 natural log u squared plus 4, and we just need to evaluate from s to infinity. But with log properties, let me rewrite this, so I can write it as u over, for the 1/2, I can create this as a square root and do it as square root u squared plus 4, evaluated from not 0, but we want this to be an s. Now evaluating this at infinity, if you take the limit of everything in here, if you take the limit as u is approaching infinity, this thing's going to be going to 1, because like before is not going to matter. And so then it's just like it all cancels to 1. So this first part's just a 0. And then we'll just plug in an s everywhere here. And so this is going to be our value for this Laplace transform right here. Let's plug this back into our equation for f of s and see if we can finish it off. Okay, now for this f of s value, I just want to clean it up before we get back to our solution. I'm going to use this minus sign to flip this. I mean, you might want to cancel the minus signs, but it's just actually I'm trying to set up a cleaner solution, so that's why I'm going to just flip this. And now at this point, we've got our f of s value. All we need to do is get back and plug in a 1 here for s in order to get back our solution to find f of 1. So let me get rid of this stuff. So now let's just plug in 1 for s here and see what happens. So we have minus 1/2. This is going to become natural log. Here, plugging in 1 here, this is going to become square root of 5. And then this is just a 1 here in the denominator, so that's nothing. And we could leave it, but I think for square root of 5, let's write that as 5 to the 1/2. And then I can take this out with log properties and multiply it times this half. So for my final solution, we just get minus natural log of 5 over 4, and that's it. Okay, there you go. Thanks everyone for watching. Have a good day.